So we know, so these are the rules that we're deriving, right? So we're figuring out these rules. And how do we, in order to figure out any one of these particular rules, how do we start? What do we do to start and figure out what these shortcut rules are? We always started the same way. Yeah? Right, so our trusted form of the rate of change is change in y for a change of x of h, right? Change of y for a change of x of h, which is f of x plus h minus f of x all over h, right? So that's our trusted form, and we can derive all these rules starting with that. But then once we derive them, then we've earned the right to use them, and we don't have to go through all that algebra every single time. We can just use the rules, right? Use the rules to find the rate of change function. So we got the rate of change of a constant, rate of change of a constant times a function, the power rule, this is the rate of change of x to the n. The sum rule is the rate of change of the sum of two functions. The rate of change of square root, 1 over 2 square root. The rate of change of b to the x, which is natural log of b times b to the x. Sometimes people will put the natural log of b after. It's multiplication. The order doesn't matter. And then this very special function where its rate of change function is the same as the amount of accumulation at any value of x, right? The rate of change, how fast the y quantity is changing, is the same as the y quantity at that moment. So that's a very, very special function. Okay. All right. So we did this example last time. That was the end of class last time, and then you got some more practice in the homework. So let's talk about the rate of change of composite functions. You should have read about this, the rate of change of composite functions. So composite function is the process of executing two functions in succession. You get an output for the first function, and that becomes the input into the second function. And we did this before when we were creating the approximate rate function. R of left of x was an example. I should say R sub f of left of x. When we came up with the approximate rate function, R of x, that was R sub f of left of x. That gave us that step function that approximated R sub f, but with constant rates, right? So this is what this looks like. First, we put an x value into the left function, and we got another x value, right? And then we took that x value and we put it into R sub f. And that gave us, who's the honor over here? Who's the honor? Where are you? Yeah, can you start that? I appreciate it. Okay. You don't have to vibrate your vocal cords. You could just let the air go in and out. Okay, so put x into left, and then left gives us another x value at the left side of the current interval. Put that into R sub f, and then that generates that approximate rate function, R. Okay, this was an example of a composite function that we saw. Okay. All right, so let's look at some examples here. So, so in order to make sense of these, we want to first look at them and break them down. So here are some composite functions. So in each case, there could be considered g of f of x. What would f be and what would g be in each case? And there's kind of some variations to the answers, but there's kind of an obvious choice in each case. So in this first one, what function? So we think of this we'll talk about this as the interior function and the exterior function, okay? The interior and the exterior, okay? So what would be the interior function of the square root of x cubed minus 5? What's the interior function? All right, so she's offering up x cubed minus 5. Okay, and that is the result of x cubed minus 5 becomes the input or the independent variable for which function? What would G be, or the exterior function? Square root of x, right? So if f of x was x cubed minus 5, and g was the square root of x, then you see that g of f of x would be the square root of x cubed minus 5. Does it make sense? If you took the result of f and then plugged that into g, you'd get exactly what m is. See that? Okay, so let's just practice for these other two first. So practice how is p of x a composite function of g of f? What would f be and g be? Same with q, the function q. What would g be and what would f be in that case? Go. So write those down and then compare with the person next to you. Okay, so for p, what is what we call the interior function? What would f be? Someone over here. What do you think? Yeah. Okay. One possibility would be 3x to the 8th. And if f were 3x to the 8th, then what is the exterior function that would give us p? What would the exterior function that would give us p be? Just e to the x, right? Anyone got a different way to do that one? There's another way to do that. Yeah.
My f was x to the 8th.
Just x to the 8th for f. If f was just x to the 8th, then g would have to be e to the 3x, right? So either one of those would work, okay? But once you decide what f is, then g is determined, right? So if f is 3x to the 8th, g has to be e to the x, okay? All right, this one, q, the interior function, what we call f, is. What do you think? 1 over x squared is an obvious choice. Then g is sine of x. So just getting the idea of a composite function. It's where you take two functions and you put them in succession, so the output of f then becomes the input into g. Okay? And we'll refer to that as the interior function, which in this case we're calling f, and the exterior function, which we're calling g. The interior function, so which comes first in the succession of the function process? F or g? F, right? F will operate on x first, and then that result, g will operate on that result, okay? Okay, so now we want to talk about what is the rate of change of a composite function? What is the rate of change of, say, when we have g of f of x? Okay, because we have different things in play here, right? We have x cubed minus 5, we have the square root of x, so there's different rules in place. So we want the rate of change of m with respect to x. So we know the rate of change of square root of x is 1 over 2 square root of x. So here's one possibility. Is it 1 over 2 times the square root of x cubed minus 5? Okay, so that would be maybe based on the rules that we know, that might be a guess that you would make. Another possible guess would be this. 1 over 2 square root of what? The rate of change of x cubed minus 5 in there. So 1 over 2 square root of 3x squared. So what I want to do is I want to show you, and I meant to do this last Thursday, want to show you how you can check when you're taking these derivatives, how we can check answers, right? So we're going to use this technique to check these two possibilities as the rate of change of m. And we want to do it graphically using GC. So how can we check with GC? All right, so I have that ready to go here, I think. Make things a little bigger. Do I need to make it bigger, or is that big enough to read? I'll make it bigger. All right, so I put the function in there. And so this is something that, especially when you're working through your practice problems, this can be, and there's going to be so many practice problems that we can't provide you with all the answers. So this is a great way for you just to go ahead and check your own answer. So what can you do? We can check it against, check our algebraic attempt, right, against the trusted form. Okay, so what is the trusted form? If my function is m of x, then what is my trusted form of the rate of change function? R sub m of x. What do we know is correct for that rate of change?
M of x minus h, M of x plus h minus M of x over h.
Good. M of x plus h minus m of x all over. Love control Z. All right. H. Is that the derivative? Is that the derivative of m?
It's the limit as h is approaching 0.
Right. So on one condition. It's the derivative on one condition. What's the condition? H is small. So we can just do that. So we're not. So we can just get the flavor of a limit by just saying h equals, say what? 0.001 or something like that, or 3 zeros if you want. But I'll just do 2 zeros should be enough. So these two statements now combined give us the derivative, right? We've got our trusted form of the rate of change with a very small h. Okay, and so then I could. And then what? So and then I want to graph what our conjecture was. Our first one was 1 divided by 2. What? Square root of x cubed minus. Is that it? Was that our first conjecture? So let's graph that. See what it looks like. Okay, it's only defined for values that make that positive, right? So that's something. This is not defined for all real numbers because under the square root it has to be positive. So here we go. And how can I now check that? So what do I want to do to check that? Yeah, I want to graph R sub m. Okay. And what should happen? If our algebraic derivative or rate of change function, the red one, is correct, then what should happen? They match up for every x values. They should be right on top of each other. How'd we do? So which one do we know is correct? Okay. We know the blue one is correct. So this attempt, based on the rules that we know so far, doing 1 over 2 square root of x, that's not right. What was our other thing that we wanted to try? Same thing, but put the rate of change of x cubed under here, right? So do the rate of change in the big picture, but then inside the square root, also do that rate of change. Let's graph those. How do we do on that one? Strike 2, right? So when we get the right algebraic rule-following derivative, we'll see like a purple graph, right? Red on top of blue, right? So they'll be exactly the same. So both of those attempts are wrong, okay? So it's something else. So let's talk about what it will be for a composite function. What will the rate of change be for a composite function? Well, we can kind of come up with that if we use our principles of the meanings of rate of change to do this. Okay? So remember this. So here's R sub f of 6.1 equals 3.8. And we've gone over this. So that number 3.8, this key value that we've worked on all semester, it means that if we have a small change in x or move a tiny bit from 6.1, the value of f will change 3.8 times as much as whatever change we picked, right? That's what we said. So 3.8, given any change in x, small one, close to 6.1, the change in the function value will be 3.8 times as much as that change that we picked. So it's got to be a small change near 6.1. So here's how we can denote that. A little change in f will be 3.8 times dx. So that mouthful up here could be just summarized with this equation right here, which is really dy equals mdx, right? dy equals mdx. Okay. All right, so now if we have this, so we have two functions, f and g, and the rate of change of f is 5 at the point 627, and the rate of change of g is 3 at 2714. And we want to talk about the rate of change of g of f of x with respect to x at x equals 6. So here we are at x equals 6, and we want to talk about the rate of change. So we let x change a little bit. And what function is going to come into play first when we let x change a little bit? We're going to look at the change in what first? F, right? The interior function. X, so we're going to say, when x changes a little bit near 6, how much will f change? How much will f change when x changes a little bit near 6? 5 times as much, right? Because the rate of change of f is 5 at x equals 6, right? So we can visually show that. So if we change the input a little bit, we can show that the change in the function f will be 5 times as much as that change in x. So now I have a change in f. And what? We're taking g of the result, or the value of f. So then what will happen, we've got a little change of the independent variable for g, because that's what the change in f is. So how much will g change? How much will g change? 3 times whatever little change we have of the independent of g. So it's going to be 3 times what you're looking at there. So when we change the input to x a little bit, we got the change in f, which is 5 times that much. But then that's a little change of the input to g. And so then g is going to change 3 times that much. So this isn't bad, right? So we're applying dy equals mdx in succession, like we said. First the function y, which has a rate of change of 5. So every change in y will be 5 times the change in x. Well, now that change in y becomes a new change in x for function g. And every change in g will be 3 times that. Okay, so thinking about this as one function, putting the two functions together in succession, thinking of it as one function, when we change x a little bit, how much does the output of g of f of x change?
R G times df.
No, in this particular example. Yeah. Does it change by 15?
For every change, 15 times whatever the change.
15 times the change in x, right? So it's going to change by 5 for f. The change will be 5 times whatever change in dx, and then for that change, it's going to be 3 times the change in x to get the change in g. So in those two steps, we get what? The output of g of f of x changes 5 times 3 as much as dx. Okay? So what is that? So we took, to get the amount, the m value, right, the rate, is going to be what? This was our 5. and then this was 3, but 3 times as much as, here's the key, 3 times as much as how much f changes, right? Three times as much as how much f changes. So this is m. This is the rate of change of g of f of x with respect to x. And so that idea right there builds our rule for the rate of change or the derivative of a composite function. A little change in x gives us the rate of the interior function, right? The rate of the interior function times as much, but then times as much as that times as much as the rate of the exterior function. Okay, so this is what we call the chain rule. The chain rule is the rate of change for composite function. It's like what we just said. So it's going to be the rate of change of the composite with respect to x is the rate of change of f with respect to x times the rate of change of g of x with respect to f of x. Okay, so with respect to f of x, that's the key. So multiplication is commutative, so order doesn't matter. So sometimes we may apply it as above, or sometimes we may apply it as below. So depending on the situation, it's kind of, are we going to work inside out or outside in? And so I find that depending on the function that you start with, sometimes one is more helpful than the other. Okay, so the way that we derived it was inside out, right? You start with the interior function, find the rate of change, and then multiply by the rate of change of the exterior function with respect to the interior. So Rg of f. Okay, but then you could work outside in. Same thing with the equation at the bottom is an outside in approach. Okay, so let's go back to this. So what did we say for that first one? We had our f was x cubed minus 5, and our g we said was square root of x. All right, so we're applying the chain rule in order to find the rate of change of m, which says do what? Take the rate of change of the interior function, or the rate of change of f. What is that? It's the rate of change of f. Our interior function is x cubed minus 5, so its rate of change is 3x squared times. Now, is it the rate of change of g with respect to x? Like, do we do the times the rate of change of that? No, it's the rate of change of g with respect to f, meaning we're going to keep that f plugged in as it is. Keep that function f plugged in as it is. So, yes, g is square root, but we're not going to evaluate the rate of change on the square root of x, but of f of x. Okay? So, we know it's 1 over 2, and here's what we mean by with respect to f. 1 over 2 square root of not x, but f as it is. So that's different than the two different conjectures we had with GC. So let's try this one now. Does it make sense what I just did? Rate of change of the interior times rate of change of the exterior, square root, but with respect to the interior, meaning leave the interior as it is inside, x cubed minus 5. So let's try that one now. So what do we have? So 3x squared times 1 over 2 x cubed minus 5, is that right? All right, so now if we did the algebra right, we know we know the blue one's going to be right. If we did the algebra right, then the red one should fall right on top of it. Okay, so we got it. So again, you could just make a GC file that looks just like this. But you might use f generically because you see f a lot more often. But it doesn't matter. It doesn't matter if it's f or m or p or q or j. And then what you're going to put in your original function here, and then you don't have to change anything here, right? This is going to be the correct rate of change function graphed. And then you'll come in with your algebraic attempt, and then they should match. So you should make a GC file like this, and this will be really helpful for you for checking as you start doing dozens and dozens of these problems. This will, and we can't provide you with a key for everything. This will be really helpful to check your work. Okay, let's practice some more. Anybody have a question? So let's do the same thing. So you have your f and g for the p and q functions that we did before. Oh, please, thank you.
If you rewrote it as x to the third minus 5 to the 1/2, you could do it that way. So I'll get the same answer.
Yeah, definitely. Yep, if you change the square root to the 1/2 power, then yeah. But you still be applying the same thing. You still be applying the same thing. So that was like when we finished doing the square root rule. We compared it to x to the 1/2, and we got the same thing. So that's you're just doing the same thing for this particular example. Okay, so for the f and g that you found for p and q, apply the chain rule and get those rate functions. If you have GC, you could build that little check file right now if you want. But let's just see how these go. So let's find the so I have to tell you sign, right? So this, in terms of getting ready for the mastery, did the TAs give you this already or not?
Yeah.
Oh, sorry. Okay. So you have this, and this gives you the rule. So we proved many of these, some of them. We're not going to prove all of them. The rest are just up to you to memorize. So the ones on the left are lots of the ones we've done already. Here's a couple new ones that we didn't talk about. Log base b and natural log. These are the formulas for the derivatives of those. Here's all the 6 sine functions, or trig functions, I should say. And then here's the inverse trig functions. So these second 2 columns are ones we haven't seen in lecture yet, and there's a couple derivations we'll do, but this is just going to be a lot of memorization and applying the rules and doing the algebra, okay, to get these closed form rate of change functions. All right, so for now, jot down, if you don't have this list in front of you, for the ones we're going to do in class today, you want to jot down sine, cosine, I think shows up. Yeah, tangent and maybe secant. If you have this whole sheet with you, just get it out. That will just be helpful. Otherwise, jot down these new ones that we haven't talked about yet. So I'll say those two too. All right. So if you jot down those 6, there's probably one I'm forgetting, but for sure those 6 will be most of the new ones that will be involved in problems that we're doing later today, plus all the ones we know already. Okay, so there's an example there, the q of x function, sine of x. The rate of change function is cosine of x. Okay, got those? Can we go back? All right, so find the rate of change of p of x and the rate of change of q of x with respect to x. Go.
Yeah, it's all.
Okay, how about back here in the green shirt? Did you get it? What's that? Still working on it. Did you just do anything on this one? Did you get started on this one?
Like having this race.
Okay, hold on a sec.
What do you want to simplify it?
Okay, we're going to regroup now. Okay, we're going to regroup now. Here we go. Did you get started on this one? (24x to the 7th). That's a good start. Good. Very good. So what? We got the rate of change of the interior function times the rate of change of the exterior with respect to the interior, meaning leave the interior function as it is. This is one of the biggest mistakes that students make, or most common. They do e to the 24x to the 7th. Okay? So just you're leaving that, when you do the derivative or the rate of change of the exterior function, you leave the interior one as it is. In this case, e to the 3x to the 8. Okay, this side, let's see. How about right here? Yep, that's you.
Negative cosine of 1 over x squared times negative 2 over x cubed.
Okay, so he's doing outside in. So outside in would be rate of change of sine with respect to the inside, meaning leave the inside as it is. So rate of change of sine is negative cosine of the input times negative 2. So we have to see that 1 over x squared is the same as x to the minus 2, right? So now we're going to do the power rule, negative 2 x to the -3, and then he changed that back to -2 over x cubed, which is fine. Yeah.
Just the cosine wouldn't be negative. The derivative of the sine of x is cosine.
Okay. So
No.
Ian disagrees, says this should be positive. Okay. So, yep. You see that? Yeah. Yeah. So the derivative of sine or rate of change of sine is just simply positive cosine. But I think we got it now. Questions on these examples? Okay, let's do some more. So do I have, okay, I think the 6 additional ones I put stars by, I think everything is included in there. Let me just write them out again. So for log base b of x, the derivative is 1 over x ln of b. The derivative of natural log of x is special case, just 1 over x. And what else? Tangent x, derivative is secant squared. And I think that covers everything. You do it on the fly.
Exactly.
You can check the first 3. Did you get the first 3 right? Any questions on the first 3? So I did outside in on both of those. That's the way it's written here on this page, outside in. Rate of change of the exterior, leaving the interior as it is, times rate of change of the interior. Okay, let's talk some structure here. What's the structure of number 4? Which rule is the overall structure of number 4? So I heard chain and I heard constant times the function. So only one of those is that structure of that thing as a whole. Chain rule or constant times a function. That's the second one. That's a constant times a function. So we know that the rate of change is going to be the constant times the rate of change of the function. Okay, now that thing, 7 to the tan x. What's the structure of that? So these are going to get really complicated really fast. And lots of rules. And so this idea of asking what the structure is always really going to be helpful. What's the structure of 7 to the tan x? So that would be our exponential function, right? That's an exponential. What's the rate of change of exponential? 7 to that thing times natural log of 7. We're done? No, but it's not 7 to the x. It's 7 to the tan x, right? So there's an interior function. The interior function is tan x. The exterior function is 7 to the x. So I just did the rate of change of the exterior with respect to the interior, and by the chain rule, I also need the rate of change of the interior. So times secant squared. So this is what? This is the exponential rule right there. But then we also need the chain rule because it's not 7 to the x. It's 7 to some other interior function. So then this is our chain rule. Does this one make sense? Okay, structure of number 5. As a whole, what one rule would apply to that as a whole? Chain rule? Okay, that's true. And so then in the chain rule, what is the exterior function? So the exterior function would be our what the structure of it as a whole. The exterior function is square root. Okay, so square root. So this rate of change function is going to be 1 over 2 square root. That's going to be essentially what the structure of the rate of change is, because the structure of the original function was square root. So the structure of the rate of change is going to be our square root rule, 1 over 2 square root. So 1 over 2 square root of what, first of all? I'm going to do the rate of change of that in there? No, I'd leave it as it is, right? I'd leave it as it is. So 1 over 2 square root of 6 times. And if you have 1/2 of this to the negative 1/2, that's the same thing, right? 1/2 of what I just wrote to the negative 1/2, that's equivalent to this. Okay? But then, by the chain rule, times the rate of change of the inside. What's the structure of the inside? Okay, so now we do the rate of change of the inside. It's like a whole new problem. So what's going to be out here is going to be the rate of change of just what's underneath the radical, like its own little problem. What's the structure of that? Sum, right? So the rate of change of that is going to be sum, or in this case, difference, right? So, rate of change of 6 times 7 to the tan x. It's this thing we did right here, right? We already did that problem. The rate of change of 6 times 7 to the tan x is the answer to number 4. It's going to go right there. What about cosine of natural log of x? We already did that problem, right? Up here. So what we end up, what happens in these problems when they get more complicated is we have problems within problems, right? So we've got rules within rules. But you just have to literally follow the rules. So we're going to do 1 over 2 square root of that times the rate of change of that. The rate of change of that is going to be the rate of change of the first minus the rate of change of the second, which are 2 that we already did. And I don't have room, so good thing we did do them before. But that would be the final answer. Again, that first part, if you have 1/2 of that expression to the negative 1/2, that's perfectly fine. Same thing. Questions on these examples? Yes?
Would it turn into plus sine natural log of x?
I'm minusing what I put a box around. So yes, it would end up being plus. Yeah. But yes, when I do put that in there, then it'd be minus would be a plus. Okay? Any other questions on these examples? All right, more rules. We haven't dealt with products or quotients of functions yet. So here's f is sine x, g is e to the x, and k is f times g. So what's the rate of change of k? What's the rate of change of k? Is it the rate of change of f times the rate of change of g? Well, in the sum it worked, right? If we had the sum of two functions, we just did the sum of the two rates of change, so it's the product of functions, we do the products of the rates of change, right? It would be nice. It's not right. Okay? That we would love that, right? It would make things very simple for us, but not the case. Not the case. Likewise, if h were the quotient of two functions, is that rate of change the rate of change of the quotient? No. Those who've had calculus before, no, it's not. Okay? But thousands of calculus students throughout the ages have tried to do this. In the midst of a harder problem, right? So we get maybe a context, and we have other things going on, and we have to get a rate of change function, and it sneaks up on us. We see this function, and we don't recognize that it's a product, and we just kind of naturally do this because we're attending to all these other things in the problem too, and so we write this down. We do the rate of change of f times the rate of change of g. It's very easy to make that mistake when this happens in the midst of a more complicated situation, okay? So don't do that. So once we get the rule for the product or the product rule, then whenever you're taking the rate of change of a product, you got to use that rule, okay? So here is a product, a generic product of two functions, f times g. What do I want? I want the rate of change of f times g of x. I want the rate of change of f times g of x. How am I going to start? What's the first step going to be? If I want the rate of change of this, again, I'm trying to focus you on this. We know for sure the rate of change of that thing that I put a box around is what? What do we know for sure? Are we still doing the absence thing if they're on there? Okay. Because lots of people should be absent today. Okay. All right. So, what would the rate of change of this be? F times g of x. What would it be that we know for sure? Yes, ma'am.
We do our trusted form
Okay, so
for the rate, or do you want me to say?
yeah, say what would it be the trusted form for
So it
this?
would be f of x plus h minus f of x.
Just look at what's in the box. So if we want the trusted form for what's in the box, what would it be? So keep your eyes on the box when you say the trusted form, because that's what we know for sure. Yes, sir.
F times g of x minus h, or sorry, x plus h.
Right.
Minus f times g of x over h.
That's right. And then that's what that turns out to be. So let me go back one. And let's write out what he said. This is what we know is correct for sure. Now look at f times g of x plus h. What is that? Now we're going to apply the rule. So what is f times g of x plus h? And we know what f times g of x is. So what's f times g of x plus h? White t-shirt. Can you tell me? What is just this much? Can you tell me what just this much is? So I want to apply this function right here, this rule, with an input of x plus h. What would it be? So what would it be? Okay, but this is function notation, it's not multiplication. This is function notation, right? F of g of our independent variable x plus h. So it sounds kind of like you're looking at that like multiplication. So what would it be? Do you know, Nathan? Okay, right. So it's going to be, we're applying this rule. We're applying this rule right here to this function, which would be f of x plus h times g of x plus h. So that's what we get. Okay, so what do we do from here? So there's really, what can we do? So there's kind of a trick to this. So that stuff that's red, so the stuff that's black is exactly what we had before. The stuff that's red is we're subtracting a function, we're subtracting an expression, and adding back in that same expression. So everything in red there is just like adding 0 on the top, so it doesn't change the value of what we had before, right? So it's like we're just putting that minus and plus in so that it maintains the equality of what we had before. And why do we do that? Because it works, okay? Because it works. Here's what we're going to do. So now we're going to gather together this first one. These first two we're going to gather together, and we're going to gather together those last two. And when we do that, we're going to see that there's a g of x plus h here, and a g of x plus h here. We can factor it out. And likewise, we're going to gather these together. And what can we factor out of those two? F of x. So I factor g of x plus h out of the first two, and I factor f of x out of the second two. And then look at what happens. What is that? Do you recognize that? Likewise. What are those two things? Yeah, the rate of change of f and the rate of change of g. So we get g of x plus h times the rate of change of f plus f of x times the rate of change of g when I now separate these into two fractions. And then we want what we want it to be exact rate of change or the derivative. So we let h get small. When h gets small, this becomes just g of x. This becomes the exact derivative of f, and this becomes the exact derivative of g. So that forms the rule. So this is what the rate of change of a product is. It's the first times the rate of change of the second. First times the rate of change of the second plus second times the rate of change of the first. That's what we call the product rule. Again, it's not the rate of change of the first times the rate of change of the second. There's a little bit more to it here. It's the first, f, times the rate of change of the second, plus the second times the rate of change of the first. So whenever you have the product of functions and you want its rate of change function, you have to use this rule. Let's practice. So when we do these, so so we recognize when we look at this function f, again, the first question we ask is, what is the overall structure of the function f? The overall structure is a product. It's one function times another. Right? Identify the structure first. So I call these g and h, right? So I call the first function g and the second function h. So what will the final answer, what form will the final answer take? The form of the final answer will be g first times the derivative of the second, h prime, plus h times g prime. Again, here's the prime notation for derivative. Remember, either Tuesday or last Thursday, we talked about there's different notations for derivative. So h prime of x, r sub h of x, dh dx. All those mean the same thing. The rate of change or the derivative of h with respect to x. So if the function is a product, the rate of change function will be the product rule. That's the moral of the story. If the rate of change, the structure is a product, the rate of change function will be a product rule. So let's write out that whole thing first, and then we just need to assemble the pieces. So what is g? We know what g is already. So what do we need? We're going to need h prime, or the derivative of h, and we're going to need g prime. So let's do those pieces separately. G prime is just 8x cubed, right? What's h prime? 6x. So now we've got all the pieces, and we just assemble it, right? We know that's going to be that's the structure of our derivative, product rule. We've got all 4 pieces, so we just write it down. Any questions on that one? Okay, try something else.
Question.
Oh, sorry.
Would you simplify it for?
For the purpose of the mastery, no. For the mastery test, you're just going to write down this first step and stop. Don't do any simplification. Okay. So the mastery test is not to test your follow-up algebra. It's to test that you are applying the rules correctly. So just apply the rule. Don't write any more. Don't do any more steps of simplification. Now, could you? Sure. You could distribute in the 6x and the 8x cubed and see if there's like terms and add them together. That'd be all valid. But for our purposes, we're not going to do any of that. If you get number 1, you can try number 2. Yeah. Is that better? Okay, so the overall structure of the first one is the product rule. But when you get to the derivative of each one of those is chain rule. So like for instance, the rate of change of p or p prime is going to be chain rule because the natural log of x to the fifth plus 1 is a composite function. So what's going to be? The rate of change of natural log with respect to x to the fifth plus 1, which is 1 over x to the fifth plus 1, times the rate of change of the interior. So this whole thing, by the chain rule, is the rate of change of p of x. So it's like a problem within a problem. Similarly, rate of change of q is going to be chain rule. Rate of change of sine with respect to radical x, which is cosine radical x, times the rate of change of the interior, 1 over 2 radical x. So those are the individual derivatives of p and q that will become part of the whole product rule, right? Because the product rule says p times the derivative of q plus q times the derivative of p, which is going to be the structure of our answer. So we're going to have p ln of x to the fifth plus 1 times rate of change of q cosine square root of x times 1 over 2 radical x. That's that. Plus q sine radical x times rate of change of p. 1 over x to the fifth plus 1 times 5x to the fourth. Questions on that? So, two chain rules that are within the product rule. Okay, so for Thursday, it will be practice